So, today we will look at the actual transport phenomena. So far we have focused on basically the equilibrium processes, that is we looked at the thermodynamics from the statistical point of view, and also a little bit about the transport process from the kinetic theory point of view. But in order to move towards a more rigorous transport process, so if you want to understand how the transport process has to be studied, so first thing you have to know about again is the distribution function. Okay. So, in the case of the equilibrium thermodynamics, so we looked at the different quantum states and then the ensemble of that. Okay. And we said there is a definite number distribution for each of these quantum state. Okay. So, if you have therefore n number of particles, so a particular quantum state, this could be quantum state 1, 2, 3 and so on. Okay. So, you have so many number of quantum states and then you have a particular number distribution n subscript I for each quantum state. So, you have n 1, n 2, n 3 and so on. So, let us say this is the last quantum state and we have n subscript omega. So, therefore, if you take summation of n I, this will be equal to total number of particles n which are distributed across all these quantum states. So, this was common in both the equilibrium whatever we have studied and also what we are going to study in the case of transport process. However, the difference is that in the case of equilibrium, each of this quantum state has a particular energy value associated with this, right. So, we talked about therefore E I, so E 1, E 2, E 3, E 4 up to E omega, but this is not sufficient to describe transport process. Okay. So, apart from your values of energy and the corresponding equilibrium distribution function that the given energy carrier can take, you also have to understand for a transport process there has to be an advection. So, therefore, there is a certain value of equilibrium distribution function which holds for systems at equilibrium or when there is no transport. But if there is a transport process, so how do we describe the distribution function now? So, for each of this quantum state, now instead of describing this with energy levels, we will have to move and use the position vector R. Okay. A particular quantum state can have a particular value of position vector, that is in a point in space. So, it can be actually located at some position and it can have a particular value of momentum. So, this is what is going to distinguish the actual transport from the equilibrium case. So, each of these quantum state is now going to be represented with the value of the position vector and the corresponding value of momentum vector. Okay. So, this is a more complex scenario that we are considering. So, therefore, if you are plotting a diagram where we plot the momentum vector in a vertical coordinate and then we have the position vector on the horizontal coordinate. Now, each of this quantum state is represented by a particular dot here. So, for example, quantum state 1 could be this, quantum state 2 could be this, quantum state 3. So, like that I can put all the points, each point representing a quantum state and plot this on to this map, and therefore, a collection of all these quantum states will be one ensemble. right. So, whatever I have represented here, so 1 to omega number of quantum states each representing a value of position and momentum. So, if I plot them onto this map of P versus R, so I have discrete points, and if I describe the ensemble of all this together, so that will be contained within this particular circle.
So, would it be closely confined or it can be scattered over the?
It should be, it can be scattered, it can be, but not so widely, okay, because what we are saying this each quantum state is more or less moving with a similar velocity and position, it is not completely off. Now how do we talk about transport here? Okay, therefore, we want to look at an ensemble of or collection of these particles occupying different quantum states, finally have to advect, okay, and when they advect, that means this ensemble has to keep moving in time, right. So, if you start from time t equal to 0, you will have an ensemble which is represented like this, and now due to advection after a certain time, then this ensemble would have traveled to this point in the this position in the PR diagram. Similarly, after a certain time, the collection of these particles would have had a different value of momentum and position and so on. So, this is now going to therefore travel like this with a definite velocity. If there had been no velocity, this would have been just here. Okay. So, this is basically you can probably think of some similar to the equilibrium distribution function, and now what is distinguishing the transport process is that you have a advection happening, and therefore, there is a change in the momentum and position vector with respect to time, which has to be now tracked and accounted for, and again the collection of these particles keep changing. So, this ensemble itself keeps changing its collective momentum and position. Okay. So, therefore, we have to study not only the average energy that is possessed by this ensemble of particles, but also the relative motion and momentum. So, this has to be studied with respect to time, and this will give the information about the transport process. Okay. So, this is on a very fundamental level, and this kind of diagram where you plot your momentum versus position vector is called a phase diagram or a phase space. Okay. So, you should understand this is a multidimensional space which we have simply plotted as P versus R, because R is a vector. So, this itself is a 3-dimensional space, and momentum is also a vector which is again a 3-dimensional space, right. So, this we have just squeezed into some kind of a 2-dimensional map, and we are trying to look at the transport. So, this kind of diagram is called a phase diagram. So, therefore, if you are looking at each particle, so how many, let us say if you are talking about this is your let us say, so this is the degrees of or dimensions, we can to distinguish this from your degrees of motion, we will call this m dimensions. These are your dimensions that you are going to look at, could be 1 dimension or 2 or 3 and if you have totally n number of particles in the ensemble, okay, what is the total degrees of number of degrees of freedom? So, let us say this is n, this is the total number of degrees of freedom small n, So, if you have m dimensions, basically m times n, then you are talking about, for example, just only the position. Okay, it can move in along translational x, y and z, for example, and therefore, each particle can have 3 degrees of freedom. Therefore, n number of particles, a system with n number of particles will have m into n degrees of freedom. Now, if you also look at the momentum also are there in 3 directions, x, y and z. So, if you also include that, the total number of degrees of freedom will be 2 times this. So, if you are including both the advection, the position as well as the momentum into the degrees of freedom, the total number of degrees of freedom that you have are 2 times m times n. So, if you are talking about 3 dimensional space, therefore, this is 6 times n, and n could be a large number of particles. So, if you are talking about Avogadro's number 10 power 23, for example, you are talking about, therefore, tracking an ensemble of 10 power 23 order of magnitude particles within time. Okay. So, this is not a very simple task. Okay. So, we will come to that. So, now what we will do is write down, for example, the equation of conservation of this particular transport process. So, if you take a control volume in the PR space, okay, so this dimensions could be dr and this could be dp. Okay, and what we are going to do is apply the flux conservation principle here, that is the net rate of particles or points, whatever you want to say, because each dot is now one quantum state represented by ni number of particles. Okay. So, if you are therefore looking at a control volume boundaries, you are looking at all these particles, which is a collection of all these points, which are collection of particles basically entering and leaving the boundaries of the control volume, right. So, therefore, if you want to write down the conservation equation, we say that net rate of particles or points flowing into control volume minus the rate of particles or points flowing out of control volume should be equal to rate of change in the number of particles, points inside control volume. So, this is like your mass conservation, just like your mass has to conserve. In the case of steady state, whatever flowing in should be equal to flowing out. Similarly, now you have a number distribution. Okay, now if you take particular control volume and apply the conservation of this number distribution, so you have these number of particles which are or points which are entering this should be equal to something going out and something which is changing within the control volume. So, if you expand this to mathematical form, we can write this as, if you represent f as the number distribution function, which you already are aware, right. This is your particle number distribution function. Only difference is that in the transport process, this is a non-equilibrium distribution function, whereas in the case of statistical thermodynamics, this was an equilibrium distribution function. Since now you are studying transport phenomena, this has to be a non-equilibrium, then only you have a transport process. So, the f now becomes a non-equilibrium distribution, and therefore, it will become a function of r and p. right, position and momentum. So, therefore, if you write this mathematically, the conservation equation will be df by dt. This is your rate of change of the particle distribution within the control volume. So, this you are writing for a system with n number of particles. Therefore, you have to use the superscript n to denote how many number of particle system you are dealing with, plus now you talk about the advection process, right. So, if you are doing a Lagrangian tracking, that is you are looking at this particular ensemble and then tracking its motion. So, it is primarily only with time, whereas if you have a fixed control volume like this in space, so this becomes an Eulerian motion. So, relative to this fixed volume, you are tracking about the motion of these particles. So, therefore, you have a change with respect to position as well as momentum, right. So, therefore, first derivative will be the rate of change with respect to the position, which will be df by dr, and now r is basically a vector. So, in the tensorial representation you can use r subscript I. So, you are tracking in each direction, and again this f is a collection of n number of particles, and the velocity here will be what? It has to advect in the position with a definite velocity. So, that is basically dr by dt. You can use r subscript I dot. So, the product of this, and now this has to be summed over all the 1 to n, because now you have n degrees of freedom. So, you are talking about a n particle distribution function. Therefore, the number of degrees of freedom in all the 3 directions will be m cross n. If you are talking about m dimensions n particles. So, therefore, this has to be summed over all of them. You cannot individually track each particle, each coordinate space and write the conservation. It has to be completely for the entire, because this r 1 2 3 represents each direction. Now, it is clubbed together as single r. That is what we have drawn as p versus r diagram here, and similarly p. And now, each particle will have definite location coordinate. So, we cannot look at each particle again. So, we have to look at ensemble of particles. So, for this ensemble with n number of particles, basically it has to be having n degrees of freedom. So, it has to be summed over all this, and this collectively should represent the advection with respect to space. The other is the advection with respect to the momentum. So, we are talking about therefore change in also the momentum as it is getting advected. So, therefore, we will have a similar derivative with respect to the momentum space p, and again for the momentum space also we have n degrees of freedom totally, and this is your derivative of p. So, again p subscript I. So, this is the second derivative, which is coming from the advection in the along the momentum plane. So, all this should be equal to 0, right. So, therefore, this is your conservation equation. If you represent a small rectangular control volume like this and use the Eulerian frame of reference, you can write down the change in the number distribution, what is happening in the position space and the momentum space, and this is your conservation equation. So, now how easy is it to basically solve this equation? Yeah.
When the summation runs from 1 to n, does the n denote the number of dimensions?
Here it is the total number of degrees of freedom. So, we have m dimensions for each particle and we have n number of particles. So, total number of degrees of freedom is small n, which is m times capital N.
So for each quantum state, the number of particles must be the same, right?
For each quantum state need not be, there is a distribution function.
Then
For an ensemble it is. For an ensemble it is collection of all these quantum states, you have n particles, capital N number of particles. So, for that ensemble is what we are actually concerned about. So, this ensemble will have a distribution function f, which is basically changing in time with position and with momentum.
sorry, for one particular quantum state, if we are having one number of particles, and for another if we are having a different number of particles, then basically in the phase space we will be having actually two different dimensions, two different number of degree of freedom.
Yeah.
Then how can we represent it in the same phase space? Space space itself will be of different having say different dimensions, right? Because corresponding to each particle there will be an R and P. So if the number of particles are different, then phase space must be different for
Yeah,
two
correct.
different quantum states.
So, you are right. So, what we are saying is now for each particle, yeah. So, the way we are looking at is, so what you are saying is for each quantum state there is a particular Ra or Pi, or for each particle you are saying
Each particle there must be an R and P, right?
correct.
So for one quantum state, if we are having some n1 number of particles, each of them there will be an RIPA. So if we represent the phase space using that, for if you need to represent say another quantum state with n2 number of particles, how can we represent it in the same phase space with the same number of RI and PA?
Yeah. So, this is one microstate you can call. Okay, this is again a small micro ensemble.
So in one ensemble, actually the different microstates must have, if it is the n must be constant, right?
The n must be constant for the macro ensemble. So, that is for this collection. So, now what you are saying is now each microstate has Ni particles. So, within that you have the particular distribution. So, that means one particle will have a particular position and momentum, another particle will have another one, and this collection is basically your Ni, which is a one microstate with a particular representative momentum and position. Okay. So, you can actually look at this breakdown into each value of momentum and position. We are representing this with one quantum state, which is a microstate, micro ensemble. And like this we have several micro ensembles, put them together you have the macro ensemble.
So suppose if it is an NVT ensemble, the different microstates means just the distribution of energy is different in the same number of particles, right?
Distribution of energy is different, yes, the actual, if you look at the actual occupancy function. So, within this, if you go within this, you have a distribution function at different values of momentum and space position. So, each particle will take up a particular value of momentum and position, and that is given by this Ni.
Okay. So what I am saying is, suppose if we
But what we are doing now, statistically, we are not concerned about tracking each and every particle's motion and momentum. So what we are doing is we are grouping this together into a microstate. And we are representing that microstate with n particles having a representative momentum, effective momentum and position. So that is one dot. Okay. Like that we have so many microstates which are all given by each of these dots. Now this together is an ensemble which is your macro state. Okay.
My point is actually if the phase space we will be if suppose if we are having three different position say x, y, z space at 3 different momentum coordinates, then if there are n number of particles, the phase space must be a 6n dimensional space.
Yes.
Yes.
So we, that's what I have written here.
Okay.
So if you have 3-dimensional space, you have 6n.
6n dimensional. So if you are having for another microstate, if you are having some n2 number of another quantum state, if you are having some n2 number of particles, how can we represent that 6n1 and 6n2 in the same phase space?
No. So for no, this is for the complete ensemble of all the microstates that should together should have the n number of capital N number of degrees of freedom. So we have n particles. So capital N number of particles. Therefore, you have capital N times m degrees of freedom should be there for the entire ensemble. Okay, and this entire ensemble is now cutting across a particular Eulerian control volume. So therefore, it is going to get transported. So its position is changing due to finite velocity, its momentum is changing due to particular value of force, that is your rate of change of momentum. So you are applying an external force which can actually result in change in the momentum, plus you can change the position due to its velocity, due to that vector. So we are tracking this particular ensemble, okay, and therefore now we are not concerned about each and every quantum state. We want to now average or sum this over the entire ensemble of these microstates. So that is why we are doing summation I equal to 1 to the number of degrees of freedom totally. Okay. So actually there is much more detailed derivation of this which I have skipped through and made it much easier for you to understand, because most of you are already aware about how transport laws are derived. So I am just giving an analogy with that to make you understand that finally it is amounting to a conservation. Only thing now, when you talk about conservation of say mass or momentum, you are only looking at say 2-dimensional space or 3-dimensional space, and therefore you have only this particular term. Okay. Now what I am saying is we are representing this 3-dimensional space in one axis and another 3-dimensional space of momentum in another axis. So therefore we also have a second derivative coming from change in the momentum space. Okay. So this has a certain significance. So I will explain that to you. So this is basically your force, the force term resulting in change of momentum. If there is no force, this term becomes 0 and this becomes similar to your classical conservation equation. So but what finally we are telling is that if you want to solve this kind of an equation, what you have to do is you have to track all the n number of particles, okay, and you have to also understand the degrees of freedom, n degrees of freedom, you have to sum them over all the n degrees of freedom, which is computationally very rigorous. So you have to keep track of all these microstates within the ensemble and also all the degrees of freedom, and therefore we should distinguish all of them and then finally sum them up in order to satisfy this conservation equation. So that is the way this equation can be solved, and practically this is not possible. Okay. So this kind of equation, this is called as Liouville equation. So the Liouville equation holds for a system with n number of particles, and this is too cumbersome to track the distribution with n number of particles. So n particle system, you have to track all the n particles, you have to understand the distribution function for each microstate and then sum them over all the degrees of freedom. So this is going to be computationally prohibitive. So we can right away say this, although this is your perfect equation, this is computationally prohibitive to solve this. Therefore, the more practical approach is to reduce this to a one particle distribution function. So like we say, you in the if you take n particles, out of that you pick only one particle and think this is a representative of n particles, like a sampling. Okay, this is good enough to represent what the n particle distribution is, and you assign this to one particle. Okay. So, now this is going to be computationally easier, but you see the number of degrees of freedom have just reduced like anything, but what is computationally feasible to solve is to look at one particle distribution. So, we have brought down all the degrees of freedom from n number of particles to one particle. So, therefore, if you are looking at 3-dimensional space, your number of degrees of freedom will be 3. So, from 10 power 23 we have brought the number of degrees of freedom to 3 if you take one particle distribution function. So, for this the Liouville equation will turn out to be the Boltzmann transport equation. So, this however has a downside. So, I can simply replace this df n by dt with df by dt, which is a one particle distribution function. These all the summations will disappear now, okay. Essentially, or the summation will have to happen in 3 dimensions, that is it. But what will happen, since you have n particle system, this conservation equation is perfectly satisfied. Now, if you remove that and you put one particle, you do not have number conservation. So, therefore, in the process we have to now add another term, which is your collision between the particles. Okay. So, when you simply reduce the degrees of freedom, it is not simplifying maybe one part, it is quite simplifying the advection part, for example, but you introduce a newer term to satisfy the conservation equation, and that is the collision term. So, therefore, neglecting all the mathematical details, I will directly give you how this one particle distribution will satisfy the conservation. So, now the term here will be in 3-dimensional space. So, you have this will be r dot I, that will be u into similar to your velocity. So, dr by dt in the x direction will be u velocity, df by dx. So, this can be simply written as what, like some velocity vector dot product with your gradient of the distribution function with position. So, this can be therefore simply written as dr by dt. So, let me use the same notation as in your textbook, so that I just still use dr by dt, and this is your vector dotted with your gradient in the R space of the distribution function, right. So, this has now for one particle simplified to a simple term, which is your transport term. Now, this is the other term, which is with respect to your momentum space, also can be written in a similar manner, dotted with del p f. That means, you have 3 degrees of freedom essentially now in each space, momentum space and position space, okay, and you are finding the derivative in each direction, making a dot product with your corresponding change of that quantity with time. However, this will not be equal to 0. To satisfy the number conservation, there will be a term which I represent like this, but this is not a time rate of change. I use this entire bracket subscript c. This means this is called the collision between particles. So, this is the change in the distribution function due to collision between particles. Or rate of change in the distribution. So, this is coming because of reduction from an n particle system to one particle system. But however, we have greatly simplified the transport equation, which now can be solved, or we can at least attempt to solve this, right. However, due to the introduction of this collision term, we have a lot of difficulties. We will see that this collision term is not simple. So, now we are talking about maybe collision between two particles, and you have a third particle which is coming out, and you can talk about collision between three particles. This is a more complex situation. So, it becomes a multi-body problem, right. So, it depends on how many number of particles you are actually looking at in a given time for to solve this collision problem. Even a simple 3 particle problem, that is 2 particles colliding and forming a third particle. So, two phonons colliding and you get a third phonon. So, 2 electrons colliding getting a third electron. So, even this is a very complex collision process. Okay. You do not have a very simple expression to model this, and we make a great deal of approximation to that. Okay. To just give an example how the collision process looks like, if you take for example 2 particle scattering process like this. Okay. So, let us say okay, before we go into that, we can write 2 or 3 different versions of the Boltzmann transport equation. Let me call this as equation number 1. So, this is your basic format. We can also write this, as you can see, this is your velocity of the energy carrier with which it is advecting, right, and this is your rate of change of momentum. Now, what is rate of change of momentum? Force. Okay. So, this is your force vector. So, the alternate ways of writing this is df by dt plus you have velocity vector. So, just to distinguish the derivative with respect to the position space and the momentum space, I use del subscript r and del subscript p. So, the other one is your force vector del subscript p. So, now this is what del subscript p is actually df by dp, right. So, this I can write this in terms of velocities also. I can replace p as mv. So, therefore, I can replace this derivative with respect to velocity and I can bring the m out. This is the mass of the particular energy carrier or particle. So, this is an alternate way of representing the force term. So, this is say equation number 2. Now, there is also another way of representing this. Okay. We also know that if you look at wave particle duality, so we from the quantum mechanics we have already derived the relations between the energy and the wave vector. Okay. And somehow we have used that also for particles. So, we had looked at electrons in a crystal, we have looked at phonons. So, for all of this we have derived the dispersion curves, which is essentially represented by relationship between energy and the wave vector. So, therefore, we can also keep moving from the momentum to the wave vector space, because many cases we have the dispersion relation, we can deal with the wave vector space. So, you can always deal interchangeably between the particle and wave aspects, and we can also write the force term with respect to the wave vector. So, how do we do that? So, you have the force vector, again you have df by dp, dp will be simply h cut k. So, we can write this as gradient with respect to wave vector space f is equal to ef by. So, therefore, all these are the same Boltzmann equation, only it depends on how you are writing the gradient of distribution function when you have a force. You can write this in terms of the actual momentum space, or you can write in terms of velocity space, or in terms of wave vector space. All these are equivalent, because momentum is related to wave vector and also to the velocity, right. So, therefore, in order to solve this equation, you need to track the particle with respect to, say, 3 dimensions. If you are doing this in 3 dimensions, you have to calculate the derivative with respect to the position in 3 dimensions and with respect to the wave vector kx, ky, kz. So, there are 3 dimensions of wave vector space. So, therefore, you have to account for 6 dimensions. So, 3 spatial coordinates, 3 momentum coordinates and 1 time coordinate. So, this becomes a 7 dimensional problem, right. So, at least a 7 dimensional problem right now. Okay. So, therefore, still this is much better than looking at 10 power 23 dimensional problem. Computationally this is possible to solve. Now, the coming back to this collision term. So, as I was describing, for a simple 2 particle collision like this. So, you have 2 particles. So, for example, you can say one particle has position r. So, and you have wave vector k for this. The other particle is also at the same position. Now, these two are colliding with each other. So, position is the same, but different wave vector. That means it can have different momentum, different values of energy. Okay. So, at time t. So, after collision, so these two will collide and a new particle is formed, and this particle will have a value of position which is still r, but the value of k now can be denoted with k prime. Okay. So, therefore, you can write the df by dt. If you do it in a slightly different way. So, I am assuming that these two are not simply colliding and forming a particle, but some kind of collision which could be either elastic or inelastic. We are considering an inelastic system in which your momentum is going to change and energy is going to change after collision. So, we can say before collision you have these 2 particles. Now, after collision, so this is going to change to r, and we will say k prime t, and this momentum is going to change to k1 prime t. So, this is particle. So, let me shade this particle 1, and this is also particle 1 after collision. This is your particle 2 before and after collision. So, there is also a scenario where these 2 particles can collide, and effectively you represent this by a third particle with an effective value of momentum and position. Okay. But in this scenario we are just saying the same particle before and after collision will have a change in the wave vector from k to k prime, and the second particle will change the wave vector from k1 to k1 prime. So, therefore, the collision term for this case is written as minus integral, you have f of r k t, this is for your particle 1 before collision, times f of r k 1 t, this is the second particle before collision, and you have a function. So, this function I will come to this, I will explain what it is. We have k comma k 1 before collision, and this changes to k prime k 1 prime after collision, and this integral is over the wave vector space. You have dk this you have k 1 k prime and k 1 prime. Okay. So, now this is a very complex integral. You have to integrate this over d cube k 1 and d cube k prime. D cube means here we have 3 dimensions. We have k x, k y, k z, and not only that. So, this becomes therefore triple integral in terms of k, triple integral in terms of k prime. So, this is k prime is after collision, and then another triple integral for the second particle after collision. This is one such integral, and you have again another integral which will be f r comma k prime. So, this is your first particle after the collision times f r k 1 prime t. So, this you can consider is the distribution before collision. So, this is your before collision term, and this is your after collision. So, the rate of change in the scattering is what we say after collision minus before collision. So, that is how we are writing this. So, this again you have the function which goes from k prime k 1 prime to k 1, and again you have the integrals 3 triple integrals. So, totally it is actually 9 integrals. We have k 1 d cube k prime d cube k 1 prime, okay, where this w function is called a Wronskian function. Okay. So, I am not giving all the details, but this is called a Wronskian, and this particular function in this case will be giving you a function to tell you what will be the change in the wave vector from an initial wave vector. For example, in this case this is pre collision and how it is related to the post collision, and similarly here post collision. So, you have due to the collision certain number of particles with a wave vector k k 1 changing to a wave vector k prime k 1 prime. So, this is going out. So, this is going out from out scattering out from a certain wave vector space. There is another distribution here which is coming in from another wave vector space k prime k 1 prime to this value of k and k 1. So, this what we call as the simplest possible collision between two particles, okay, is represented by a very complex scattering integral. Okay. So, as you can see these are all integrals, and in collection they are called the scattering integrals. Okay. So, you are talking about therefore 9 integrals here, correct. So, therefore, this again computationally people have never attempted to solve this. That means, you have to keep track of the wave vector before collision, after collision for each particle, okay, and then you are now talking about calculating 9 integrals, okay, and therefore, this gives you the collision between just 2 particles. Again the more complex scattering integrals are there for 3 particle collisions and so on. But why I want to emphasize is just to understand the sheer level of complexity when you deal with the simplest possible collisions. So, this is a computationally prohibitive task to calculate the collision terms even for a 2 particle system. Therefore, a huge simplification of this is made. Okay. So, we will talk about that in the next class tomorrow. So, but what I want to say is look at the levels of simplification that we did, starting from a capital N number of particles to one particle, and again the collision is now completely approximated to something very, very simple. Okay. But still the resulting equation is still called the Boltzmann transport equation with a relaxation time approximation. So, the original Boltzmann transport equation is this one with a very complex scattering integral. However, to solve this practically we replace the scattering integral with a what we call as a relaxation time approximation. Okay. So, that is what is generally solved to describe the transport problem. Okay. So, we will stop here.